Austin is right.
All right, unfortunately, I went to Costco in order to get you guys fruit snacks, but I asked my wife to give me to send me a list, and she didn't put fruit snacks on the list.
Yeah.
I'll try to have them by Wednesday. I found Dirac's book where he describes Dirac brackets, the second kind of Dirac brackets. And it turns out it's available on b-ok.org. And what's interesting is that his attitude was that scale of field theories weren't enough, that obviously he had invented the Dirac field also. And he knew about how important gauge fields were. But he also thought that there were all sorts of infinities in quantum field theory, and if you're going to get beyond those infinities, you'd need to have a more general class of theories. And in fact, at that time, or I don't know what the sequence of events was, he wrote several books. He considered quantum theories of extended objects and was considering things very much like membranes in string theory. And I remember reading his one of his papers on that subject, and he started out with just various introductory remarks and then said, now if we're going to have an action principle for this theory, we'll need to formulate the theory in a way that is reparametrization invariant. And this was way before string theory. This was in the 60s. And so it's, if he hadn't grown old and died, we might by now have a totally different view of physics. All right, well, today what I prepared to talk about is I'm going to review what I said last time because that material is so unfamiliar. So let me just remind you, of course, we have, for an ordinary Lagrangian, we have momenta that are conjugate to the coordinates, and we have a Poisson bracket that's defined as the sum over all the coordinates, partial A, partial Qn, partial B, partial Pn, minus partial B, partial Qn, partial A, partial Qn. And what Dirac said, and the remarkable thing is that it's Dirac who said this. He originally, back in the 20s, Heisenberg and Schrödinger were inventing quantum mechanics, and they realized that you needed you needed commutation relations, and strictly speaking, equal time commutation relations, of which this is an example, and of course there are many others. And what Dirac realized was that the quantum commutator should be IH bar times the corresponding classical Poisson bracket. And the remarkable thing is that some years later, he introduced the Dirac bracket and generalized that. Here I wrote the Poisson brackets for a mechanical theory. If instead one is dealing with a field theory, then what one has is a, what one does first is promote n to a variable a, which is n and x, and so pi a is pi n of x, which is partial L, partial pi n dot of x. And then this, I see we have a typo. This then becomes a sum over n, an integral d cubed x of partial a, partial phi n of x, partial b, partial pi n of x, minus partial b, partial phi n of x, partial a, partial pi n of x. So that's the Poisson bracket generalized to fields, and what one does if one has a Hamiltonian that's quadratic in the, or a Lagrangian or an action that's quadratic in the time derivatives, the period of the coordinates or the fields, then one can define a Hamiltonian as simply a sum of pi n dot minus L, and there's no trouble doing that because if the action's quadratic in the time derivatives, one can express the time derivatives as some functions of the fields and the momenta, and so one can re-express the action density of Lagrangian in terms of pi, and so this is h of phi and pi. In general, though, you can't do that, and of course, in general, one also has the Lagrange equations, which, let me make sure I get all the signs and indices right. It would be partial of, well, I put in a mu, let me go back to I, phi n equals partial L partial phi n. So that's, these are the field equations, and in the case where the action is simple or graceful, everything like this works fine. But Dirac in his book gives us a very simple example of a case in which this doesn't work, and his very simplest example is just L equals Q. Suppose you have one coordinate. Okay. Well, if you try to, if you compute pi, you get pi is equal to 0. You try to compute this, there are no derivatives of Q, and so the left-hand side is 0. On the other hand, the right-hand side is 1. And so he points out you get an absurd equation. By the way, you know, I've been teaching this seminar on writing, something that I think should really be a very short course of maybe a half semester rather than a whole semester. And of course, it's only 1 hour a week. And one of the things I noticed was that the people who are professors at, did I tell you guys this, the professors at Harvard, I noticed were all excellent writers. And my first thought was, well, it's just these guys are so smart that they can do both good physics and good writing. But I've subsequently taken a different view. I think it's instead that people who write really well, they have articles that are noticed, talked about these people get promoted to be professors at Harvard. Whether this is exactly true, I don't know. When I was a graduate student, I know I thought the exact reverse was true. the only thing mattered was having the right equations and being able to, you have some logical way, for example, in the 20s of getting 13.6 eV as the ground state energy of hydrogen, then no matter how your writing was, you'd be fine. But I think this is true. And then I learned something over the weekend, namely that George Kennan, who wrote a telegram from Moscow to Washington back when he was an ambassador to the Soviet Union in the Second World War and shortly after, he sent a long telegram, and in it he said that we should have a policy of containment with the Soviet Union. He subsequently changed his mind and thought that we overreacted to his telegram. But his telegram had an amazing effect. It was so well written, something I didn't know, I only learned this weekend, that he was one of the best, some people think that he was one of the best writers in America in the 20th century, which is quite a lot to say. In any event, his telegram had a huge effect and affected American foreign policy for the next, what, we're talking the 40s until now, that's 80 years. So it dominated American foreign policy for 80 years. Why? Because it was well written. So in other words, writing has this amazing effect on conveying information, and the success of a physics article or of an article about anything really is influenced more than I had ever thought by how well written it was. Anyway, Weinberg did the example of the massive vector boson, so you have Fik minus a half Vi minus Ji Vi. If you do that, then you find that pi 0, which is partial L, partial V0 dot, that's 0, that's one constraint. And then one of the equation of motion for the field V0 is partial L, partial Di V0 equals partial L, partial V0. Where's the 0? It's up there. And this is equivalent to, as you know, the analog of Gauss's law for this theory, which is m squared v0 plus j0. And that's a constraint because if you think of pi and phi as the basic variables, this involves just the spatial derivatives at time t, and this is the field and the current at time t, and so this, of course, is a constraint. And of course, this is obviously also a constraint. And it's characteristic of gauge theories that one has constraints. Okay, so let me, now Dirac knew all this and more, and so he said, well, first you have to make a list of your constraints. And then you have to distinguish between first-class constraints, and these are constraints whose Poisson brackets with all the other constraints vanish. So these are called first-class constraints. So the first-class constraints are ones that whose Poisson brackets with all the other constraints vanish. Now, if you compute this Poisson bracket, obviously you don't put in the constraint equations before you do the Poisson bracket, because otherwise all Poisson brackets would vanish. Okay. So you only impose the constraint equations after you do the Poisson. You calculate the Poisson brackets, then you impose the constraint equations, And if there's zero, then these are called first-class constraints. And in general, the solution to what one does in such cases, so let me rewrite this. For first-class constraints, one chooses a gauge. And that gauge is a gauge that then satisfies the first-class constraints. After you've satisfied the first-class constraints and effectively eliminated them, you then define a matrix of Poisson brackets of second-class constraints. And I'll show how this works in electrodynamics. Weinberg did the example of both the massive vector field and the electrodynamics. I talked about the massive vector field last time. I'm going to talk about electrodynamics this time. So you make this matrix, and in terms of this matrix, this matrix, it turns out, it tends to be non-singular. Let's say when it is non-singular, one can define the Dirac brackets, because the Dirac bracket is defined as the Poisson bracket minus a sum over A and B of A with chi A, C inverse AB, chi B, B, Poisson. And this is Poisson. And this is the inverse of this. And so this is a little bit elaborate. And in particular, this Dirac bracket is, of course, anti-symmetric. In fact, it inherits all the algebraic properties of the Poisson bracket. So it's anti-symmetric. It acts kind of as a derivation, which is AB and, of course, the Jacobi identity, A, B, C, D, D plus, and then cyclic permutations. So B, D, comma, C, A, D, D plus, C, comma, A, B, D, D, 0. Let me make sure I've got the right. Yeah. All right, and so then what Dirac said was, take the quantum commutator and set it equal to IH bar times the Dirac bracket. And so that's Dirac's rule for quantization. All right, so let's see how this works for QED. And so in QED, it's like the massive vector theory, but there's no mass. And so we have L is equal to minus a quarter Fik. I've put the stuff that I've said so far is on the class web page in it's sections 3.6 and 3.7 of the class notes. So it's not way in the end, it's just before effective field theories. Okay, minus J0, A0. And so the usual rules give the momenta as pi I as partial L, partial E0, AI, and the usual commutation relations as AI of X and T, pi I don't know why Weinberg uses uppercase letters, especially since these things are going to be so this is what we would get, and so let me put question marks on these things. That's a definition, so maybe I'll put a third line here. And the commutation relation that one would get from the usual rule would be this.
So is the idea in this Lagrangian that we don't have currents?
I'm sorry, give me that again.
You have J0, A0 there?
Yeah, yeah.
Lagrangian, so we're just no currents, is that the idea?
Well, think of it as a classical current, or it involves fermions. It doesn't involve A0 itself.
Oh no, I mean like, but there's only the J0 term, right? We don't have like J1, 2, 3, which would correspond to physical currents.
Oh, I'm sorry. Yes, you're absolutely right. This is a right-o. I mean, that's just, I just typed it wrong.
Okay.
So it actually was a typo.
Okay.
Thank you. That's really important to point out. What we see is that we've got two constraints. One is pi 0 is equal to 0, and another one is effectively Gauss's law. The divergence of pi minus J0 is equal to 0. So we have two constraints, and it turns out that these are first class. That is to say, they're Poisson brackets with each other, and with any other constraints that turn up are going to vanish. And that's not totally trivial, but it's very important. This is Gauss's law, and what you can do is you can check, and in fact, maybe I will go through this just for a moment here, because Weinberg does do that in detail, and it's certainly worth doing. So let me, oh hell, I didn't. All right, wait a minute, I forgot some notes. Let me get them. Yeah. All right.
Can I ask you a quick question?
Yeah.
Begin again. Yeah. So this notion of first-class constraints, you're saying that all Poisson brackets with each other and any other constraints vanish, right? That's the idea of. That's the idea of a first-class constraint.
The idea of a first-class constraint is that it's Poisson brackets with all the other constraints vanish.
Yeah.
Vanish.
Mm-hmm, mm-hmm. But then, so we don't use these same constraints whenever we build up this C matrix.
That's right. That's right. Right. You'll see that in a moment.
Okay.
What we do is we figure out which constraints are first class. We then massage the theory to get rid of those constraints.
Okay.
So we have a reduced theory that doesn't involve those constraints,
okay,
because we've already respected those constraints. And then we apply Dirac's bracket to the reduced theory.
I see.
So in particular, let me just mention one reason why this, which of course is Gauss's law, so the reason that Gauss's law, one of the reasons that Gauss's law is a first-class constraint is that its Poisson bracket with the Hamiltonian vanishes, which means that it's time independent. That is to say, if you have Gauss's law true at time 0, it'll be true at any time. And that's important. And so if we just look at that thing, what we have is d0 of di partial L partial fi0 minus j0. And that's minus di d0 partial L partial f0i minus d0 j0. And this is then di dj of partial L partial f ji minus di ji minus d0 j0. So in other words, we're summing here over all 4 values of I, and we then get here, and this part is 0 because f is anti-symmetric. And so what we have is simply that this is equal to minus di ji minus d0 j0, which is automatically 0 by current conservation. So current conservation gives us that Gauss's law is time independent. And that's and since it's time independent, its Poisson brackets with the Hamiltonian vanishes. Because in fact, the way Poisson brackets were first invented is that the Poisson bracket of a variable with the Hamiltonian would be the time derivative of that variable, and that was the original use of these. And so what we do then to satisfy these first-class constraints is we pick a gauge, and of course there are many, many gauges. There is the Lorentz gauge. There is the Coulomb gauge, and this is the one we're going to use. There is the temporal gauge that I talked about a few days ago. There's the axial gauge, in which people, for some reason, always pick the third direction, I guess, because it's up. And then there's a unitarity gauge, which is that the scale, some scale of field is real. Right? So we'll forget about that for a moment. And so the gauge that Weinberg picks is, for this particular example, is the Coulomb gauge, which is del dot A equals 0. This is the most physical gauge or the most commonly used gauge for, I guess it is the nicest gauge for electrodynamics. So what happens is that the constraint equation here, in the case of the Coulomb gauge, the constraint equation is minus di fi0 equals j0, and this then, since the divergence of A is 0, this turns out to be minus grad squared A0 equals j0. And so consequently we can solve for A0 of x and t as an integral d cubed y j0 yt over 4 pi x minus y. And so that's how we deal with the first-class constraints. In particular, this formula respects Gauss's law, and by replacing A0 with an integral over J0 everywhere in the action and the Hamiltonian one gets rid of A0, and also one just sets pi 0 equal to 0. So now the question is, what do we do with the remaining second class constraints? And so the second class constraints what are the second class constraints? One of them, chi1x, is di ai of x and t is 0. And the other one is Gauss's law, di pi I of y and t plus J0 of y and t equals 0. Now, I am a little puzzled. I thought these were the... I'm just a little confused with the logic here. One of them... Well, these are the two secondary constraints, and what I'm a little puzzled about is I was calling them first-class constraints over here. And so now I've got I must say, I've got well, let me go on with this in any event. Let me form the Poisson bracket of these two second-class constraints. And, as I said, I'm a little bit puzzled about calling the same constraint first class in one place and second class in another. And
do you have a difference of
what?
Sign?
Do you see what the
well, I don't know. I mean, is there a difference of sign with? I mean, at least with the J. Oh no, but that's upper and lower indices. Yeah, so that doesn't matter.
Yeah.
That doesn't matter at all.
That's the least of it. All right, there are actually two terms here. There's first and second class constraints, and then there's primary and secondary constraints. And I may have gotten something wrong. In any event, what one does for electrodynamics is one fixes a gauge, one gets rid of A0, and then one has these two second class constraints. And so now the thing to do is to compute. I think what I said over here, I hope I said it, was that one takes the second class constraints, forms their Poisson brackets, and then defines a matrix of their Poisson brackets, then defines the inverse matrix of their Poisson brackets, and then defines the Dirac bracket in terms of the Poisson bracket, and that long expression there involving the inverse of the matrix of Poisson bracket of second class constraints. So, in any event, the thing I want to look at is chi1 of x and t with chi2 of y and t, Poisson. And by this, what I mean is chi1 is that, and so this is di ai of x and t with this one, which is that. And so that is, let's say, dk pi k plus j0 of y and t. And we're looking at the Poisson bracket of that. And so that is going to be a sum on I and k of an integral d cubed z. And now this is going to be the partial of, let me just write it as divergence of a of x and t. So I guess I'm not going to need to sum over quite so many variables there. All right, I'm using vector notation, so there's no need to sum. Actually, there is a sum on I. Partial ai of z, partial del dot pi of y and t plus j0 of y and t, partial pi I of z, and then minus things in the opposite order, which are partial of del dot pi of y and t plus j0 y and t, partial ai of z, partial del dot a of x and t, partial pi I of z. So that's what the Poisson bracket amounts to. And now you can see that the second term is just 0, because J0 involves the matter fields. So just matter fields. And actually, in the case of a scalar field like the Higgs, things may be more complicated. But here I'm just thinking of a simple case where J0 is just matter fields. So, this term is 0, that term is 0. We just need to compute this. And then the way we compute these is to use these equations. The partial of del dot A of x and t, partial ai of z, and this is di of delta cubed of x minus z, and partial of del dot pi. So, by the way, that when I went on about J0 just involving matter fields, that means we can ignore J0 when we compute this partial derivative. And so this is just del dot pi of y and t, partial ai of, no, this is partial pi I of z and t. And I see I've got a typo. Yeah, typos there. And this turns out to be partial I delta cubed of y minus z. And so now putting these two together, we get that C1x 2y, which is the commutator chi1 of, say, x with chi2y, Poisson. This is then a sum on I integral d cubed z, and the first term is di of delta cubed of x minus z, and the next one is di of delta cubed of y minus z. And now delta functions are defined so as to permit integration by parts basically everywhere. And so integrating by parts, we get that this is a sum on I integral d cubed z, let us say delta cubed of x minus z minus grad squared of delta cubed of y minus z. And now doing the integral over z, we just replace z by x. And so we get that this matrix element is minus grad squared delta cubed of x minus y. And since it's grad squared, we don't have to look more carefully to see whether it's derivative with respect to x or whether with respect to y. It doesn't matter, they're both the same. Of course, this thing is anti-symmetric, so C2y1x equals minus C1x 2y. And you can check that C1x 1y is 0, and the same thing is true for 2x 2y. So the other things vanish identically. Why is that? Well, if you had chi1 of x with chi1 of y, you'd have a del dot a here and a del dot a there. Well, the del dot a with pi would give you a vanishing partial derivative. And then down here you'd have another vanishing partial derivative. And the same thing is true if you use chi2, because then you'd have del dot pi and j. Well, j doesn't play any role in the Poisson bracket, so then you'd have a del dot pi and an a, that's 0. And then over here, you'd also have del dot pi and a, which is 0. So these two relations are very easy to understand, and they are 0. All right, let me show you what the inverse matrix is. We have to compute it now. I will straighten out this first class, second class, primary, secondary thing tonight or tomorrow, and put it on the class web pages. Okay, so now we want to figure out what the inverse of this matrix is, and it turns out that the inverse matrix, and let me just make sure I don't have a minus sign missing. Yeah, I do have a, well, no, that's right. Where's the answer? Oh, the answer's down here. The minus sign is there. So what is the inverse of this thing? And so the idea is, all right, let me give you the answer. C inverse 1x 2y, so that C inverse 1x 2y, this turns out to be minus the integral d cubed k over 2 pi cubed e to the I k dot x minus y over k squared, which is minus 1 over 4 pi x minus y. So what we finally wind up with after doing the inverse is something that is very familiar and something we're very happy to see. And what's remarkable is that Dirac somehow realized that this long chain of very general and abstract reasoning would give us something as simple and welcome as that. Why don't we just check that this works? So let's multiply this thing. And the way we're going to do the multiplication, I think, is I'm going to change y to z here. So I'm going to do an integral d cubed z. And I'm going to here have minus grad squared of delta cubed of x minus z. So that's going to be this. And then up here, I'm going to have minus this thing, which is integral d cubed k over 2 pi cubed e to the I k dot, and now I'm going to have this z minus y over k squared. All right. Now, what I want is that this is delta cubed of x minus y. And the minus signs cancel. Whoops. Minus signs don't seem to be canceling so well. All right, here we come with our grad squared. Ah, yes, the grad squared brings down 2 i's. So the minus signs cancel. The grad squared comes in here, pulls down minus k squared. The k squared cancels, we get a minus sign. And so this left-hand side is then just an integral of, and then of course we also, all right, so maybe I should do this in 2 steps. So I'm going to do the minus grad squared, and I'm going to keep delta cubed of x minus z. The minus grad squared, well, the grad,
I think you want to integrate by parts, which introduces yet another minus sign, right? And then in the end you get 4 minus signs overall.
yeah, okay, now I've gotten, I'm canceling these 2.
Yeah.
I'm doing this z thing, and it comes over, and so I'm going to have integral d cubed t k over 2 pi cubed, and what I've got is the k squared cancels, but I've got a minus sign.
But you get another minus sign because didn't you just integrate by parts?
Yeah, but you integrate by parts twice.
Oh, you do it twice. Oh, damn. Yeah, that's true.
Well, where's the k squared disappeared? The k squared,
Yeah.
well, where disappeared?
Well, when the grad squared, when grad hits this, it brings down an ik. Ik squared is minus k squared. The k squared cancels, but I'm left behind with a minus sign.
Is I squared? Since it differentiates that part, so there's an I squared.
Yeah, that's the 3rd minus sign.
All right, wait a second. Of course, it's possible it's a typo in mine, but in any event, we do the z integration, and that just gives us this, and so this is plus or minus delta cubed of x minus y.
Yeah. You totally should not.
Well, it could be that I computed something wrong here. Might be a minus sign loose here. Oh, I don't see it. This is... All right, let's keep track of what these derivatives are. This is a derivative with respect to y, right? And so we have a plus there. This thing is a derivative with respect to x, so we have an x derivative. So let me just put in the x's and y's carefully. So then here, this is x, and that's y, right? And All right, when we switch from d by dx to d by dz, do we inherit this minus sign? I think so. So let's say we inherit that minus sign, then we get a minus sign d by dz, then we integrate by parts. And so this thing would be a d by dz. All right, look, I will try to straighten this out tonight, try to get this minus sign straightened out. It's clear that it's approximately right, within a plus sign or a minus sign. In any event, let's now use what Dirac told us. What is the Dirac bracket? Well, it turns out that if you then compute AI of x and t with pi j of y and t, Dirac, what do you get? Well, you get the Poisson bracket, but then you have to subtract. So let me write down what this whole thing is. It's AI of x and t, pi j of y and t, Poisson. And now this thing gives you, as I recall, the naive answer, which is just delta ij, delta cubed x minus y. But then we have to subtract AI of x and t, and it would be this chi1 z, say, C inverse 1, and now I want to use two indices, 1z, 2w. And so this is an integral. Chi 2w with pi j of y and t. And this is Poisson, that's Poisson, and that's this inverse thing, which is just this. Okay. The first term gives us, oh, and we're going to write, this is the Dirac bracket, so we're going to write IH bar in front of this. So this is for the quantum commutator. IH bar times the, well, let's get rid of the H bar because we've got enough chalk on the board. Let's get rid of the H bar, I mean. So what we have here is I, delta ij, delta cubed of x minus y, and then this whole thing, what is it? Well, the AI with chi1, let's see, where did we compute that? Where did we compute? We computed AI with chi1 somewhere? All right, well, let me just write down what the answers are. Just AI of x, chi1 of y. This turns out to be minus d by dxi, delta cubed of x minus y. And pi I of x with chi2 y. And these are Poisson. This is equal to partial xi of delta cubed of x minus y. And now that I think about it, this is kind of obvious. All right, anyway, we get these two things we put them in here, and we use this inverse, which is that, and this would be z minus w. It turns out that the whole thing is the transverse delta function. In other words, what we have here is partial xi, partial xj, 1 over 4 pi x minus y. So this gives you the, this means then that the commutation relation for ai with pi j is the transverse delta function rather than the ordinary delta function times the Kronecker delta function. Was that a question?
Yeah, so if you're making this I times that, then shouldn't we get rid of the subscript d on the, so this should be the quantum commutator, not the Dirac.
Yeah, you're right, yeah. Okay, and if you, what you can check is that the commutators of AI with a j and pi I with pi j, these are both 0. Now you might say, how does one get, how should one think about this? Well, you remember when we first talked last semester about the quantizing the electromagnetic field, what we said was that, let's see, I hope it's in when I, if not, I'll just write down, yeah, I think it's here. So, what we've got here for AI of x and t is we have a sum over two polarizations, an integral d cubed k, square root 2 pi cubed, 2k0. We have an a of k, and let's see, what should I use as a polarization? Let me just use s equals 1, 2, s, epsilon s of k, e to the I, k dot x, plus a dagger of k and s, epsilon s star, although you can typically choose them real if you want. And so this is the electromagnetic field, and these epsilons are such that k vector dot epsilon of k and s is 0. Well, I have a subscript, so. And consequently, these are two orthogonal unit 3 vectors, not 3. And so when you take the commutator, what you get is a transverse delta function if you apply the usual commutation relations with, let me see what we're doing for, I forget exactly what pi is in terms of the creation annihilation operators.
Pi is just the time derivative of that.
I would, that's what I want to say, and I think that works. So I think we can just say here pi I is just AI dot, and I think then if you do that, that's how you get this transverse total. So I'm sorry about leaving certain things and other things a little bit, rather a lot, up in the air, or, well, let's see, we're sort of out of board space here. One of the things, you know, when you switch from the operator formulation of quantum field theory to the path integral formulation, some things get easier, some things get harder. One of the things that gets easier is this business of quantizing gauge theories. In a sense, at least, it gets easier. First, so let me just start this. The Hamiltonian that you get here is the ordinary matter Hamiltonian plus an integral here of a half pi squared. Oh, that's right. I didn't tell you how you compute pi. How do you compute the Hamiltonian? The Hamiltonian here, the usual thing would be pi dot a dot minus L. Well, we're in Coulomb gauge though. So pi dot, A is transverse. And consequently, pi is transverse in this expression. And then we're subtracting A dot squared, and A dot is effectively pi transverse in this. In any event, what one gets here is a Hamiltonian that is an integral of pi squared over 2 plus curl of A squared over 2 minus A dot J d cubed x, and then plus a Coulomb term, where the Coulomb term is a half integral J0x J0y d cubed x d cubed y over, let us see, how much is it? 8 pi. Well, no, 4 pi if we have a 1/2. 4 pi x minus y. Okay, so that's the Hamiltonian. Well, what I should say is it's H matter plus this. So it's this plus H matter. So the total Hamiltonian is H matter Coulomb term, and then this thing that only involves the transverse electromagnetic field. And so that goes up here, which is a half curl. This is just B squared and minus J dot A plus a Coulomb term. Okay. And so what one has in the usual way is the time-ordered product of fields this isn't working very well. Let's see if this one works. Oh, it works. You know, it's funny. This one works dry, whereas the one that just now doesn't work, didn't work, works if it's wet. So what we have then is vacuum time-ordered product, a bunch of operators. So this is a time-ordered product. Well, this is time-ordered. Over here, it's just a product of classical variables, effectively. E to the I, the action, and in the Coulomb gauge. A Coulomb gauge condition, and then integration over matter fields and gauge fields, and then we divide by EPISC gauge condition dA d psi. And so there's a trick. And the trick is you multiply this by something that I call F. F for fudge factor, e to the I over 2 integral gradient of A0 plus gradient of inverse Laplacian times J0, all of this squared, d4 of x, integrated over A0. So this fudge factor is you introduce a new field, A0, the one that you eliminated, the one that we eliminated when we fixed the gauge. So we introduce it here as a mathematical convenience. And that thing is also integral e to the I integral a half grad A0 squared minus A0 J0. And then this other thing turns out to be I d Coulomb integrated dt, whereas all of this is integrated d4 of x. So there's a d4 of x integral of that, and then a Coulomb integral here. And if you multiply top and bottom by f, what happens is that the Coulomb term cancels, and this thing, well, I'm just going to multiply by f like that, and then this thing is equal then to an integral O1 to On e to the I s prime, still the Coulomb gauge condition, dA d psi e to the I s prime Coulomb gauge condition dA d psi, and now s prime is an integral of a half a dot vector squared minus a half curl of a squared plus a half grad A0 squared plus a dot j minus A0 J0 plus the Matter-Lagrangian, all that d4 of x. And so this delta function, though, enforces the Coulomb gauge condition, and so we can add a term to the action, or essentially anywhere else. And the term I want to add is del dot a dot A0, which is the same thing as minus a dot grad A0. And when we do add that, then it can combine with this term, and we then get that S prime can be replaced by S, which is just 1/2. In fact, it is, okay, so it's integral 1/2 A dot minus grad A0 squared minus 1/2 curl A squared plus, and now it's the relativistic AIJI plus Matter-Lagrangian D4 of X. And so this is the gauge invariant action with the matter field, all of that, and the only, and we can eliminate the prime now, and the only sign of the Coulomb gauge condition is the delta function that enforces it. And there are then two ways of dealing with this. And I think what I'll do is I'll postpone these two ways until next time, because we're sort of out of time, and it's a little bit subtle. So let me just write it up there.
Yeah.
All right, so there are some sign errors, some signs that are
Should I close it?
that I'll try to get straight. Is there a question? Yeah, stop it.
After the question.
Question.